Hey guys, first things first, I just wanted to apologize about the previous video with the mix-up about the due date for the test. And again, I promise I'll be a little bit more careful with that. The thing is because I'm actually filming the majority of the first, I want to say, 7 videos over spring break. So I'm planning way, way, way ahead in advance. And of course, I'm uploading them onto YouTube, and I mixed up on the date. So I sincerely apologize. Anyway, another thing I want to mention is some of you guys may have noticed that if you look, maybe if you looked up logarithms on the internet or if you looked them up in a textbook, you'll notice that a textbook uses lowercase letters and I use uppercase letters to distinguish a log. And it's no big deal. It's just that the reason why I use capital letters is it's surprisingly it's been more than one student who have said, why do you keep writing the number 109? And so apparently the way that I write lowercase log, the lowercase, logarithm that you see in a textbook, it looks like I'm multiplying a number by 109 every single time. So to avoid that, I've used capital letters log just to make sure that we're talking about logarithms, not my weird fascination with the number 109. Okay, so I apologize if that confused you. Anyway, so today's unit is this next upcoming unit is the properties of logarithms. In other words, our goal is to be able to prove the big three log expansion formulas. So question one, there's going to be 3 questions today. Is log of a times b equal to log of a times log of b? So in other words, if I have a multiplication problem inside of a logarithm, can I separate the two factors with their respective logarithms? Okay, so I did 2 examples with this. The first one involving base 10. So for instance, I just said, suppose that the log of 10,000 times 1,000 is equal to the log of 10,000 times the log of 1,000. Well, what that means is 10,000 times 1,000, I just counted zeros, that would be 10 million. Okay, so 10 million, we know our theory about logarithms. Since there's no base, it's automatically base 10. Well, log of 10 million, 10 to what power is 10 millions? 1, 2, 3, 4, 5, 6, 7. That would be 7. So let me get my red. So log of 10 million is 7. The log of 10,000, count the zeros if there's a 1 in front. So 10 to what power is 10,000? That would be 4. And finally, log of 1,000, 10 to what power is 1,000? That would be 3. So according to our quote-unquote theory, log of 10 million should be equal to log of 10,000 times the log of 1,000, which would make it seem like 4 times 3 is 7. So I don't know about you guys, but 7 does not equal 12. Okay, so the question is log of a times b equal to log of a times log of b? Well, apparently not if we use a basic example of 10,000 and 1,000. Does anybody have any ideas what's the relationship between log of 10,000 and log of 1,000? Log of a times b. Okay. Well, I don't hear anything because I'm just recording and you're not talking to me, so I'm gonna move on. No, I know what it is. I'm just messing with you. So let's try another example where it's not base 10. Sorry, where the argument's not some sort of base 10. So let's go with something like the log of 6 times 8 is equal to the log of 6 times the log of 8. So I'm going to need my calculator for this. Let me just make sure. Where did it go? Aha, there it is. So for instance, I know that the log of 6 times 8, I can break 6 times 8 into 48. And I've got log of 6 times the log of 8. Well, if I plug in the log of 48 in my calculator and I enter. I'm just going to round to the nearest 3 decimal places. I know I said 5 in the previous, but just bear with me. Let's use 3. So I've got 1.681, 1.681, and if I plug in the log of 6 in my calculator, I get 0.778. And if I do log of 8 in the calculator, I'm going to get 0.903. Okay, so apparently, if I multiply log of 6 times log of 8, I should get log of 48. But the more I look at it, I've got a number less than 1 times another number less than 1. So for some reason, I get a number bigger than 1. I just don't see that happening. So there's got to be a relationship between 4, 3, and 7 that doesn't involve multiplication. And there's got to be a relationship between 0.778 and 0.903 to get to 1.681 that doesn't involve multiplication. So does anybody have any ideas? I have a theory that if I add these two, I'm going to get 7. And if I add these two, I'm going to get 1.681. So why don't I try that? I'm going to add 0.778. And 0.903. And I get 1.681. So I'm going to write down, I think, adding will work. That's just my theory. And it turns out that I'm right. Okay. All right, moving on to question number 2. If I have the division inside of a logarithm, log of a over b, is that equal to log of a divided by log of b? So for instance, I just picked 1,100,000. So if I did the log of 1,000,000 divided by 100, is that equal to the log of 1,000,000 divided by the log of 100? So I'm going to break down the left side. If I cancel out 2 of the zeros, that leaves me with 4 zeros. So that's log of 10,000. So apparently the log of 10,000 should be equal to the log of 1,000,000 divided by the log of 100. So now that it's all in base 10, I'm going to see if this rule works. Well, I'm going to do this piece by piece. 10,000, log of 10,000, 10 to what power is 10,000? That would be 4. The log of 1,000,000, well, 10 to what power is 1,000,000? There's 6 zeros, so I'm going to put 6. And then the log of 100, 10 to what power is 100? Well, 10 to what power is 100? That'd be 2. So therefore, apparently, 6 divided by 2 is 4. And I don't know about you guys, but I don't think 4 is equal to 3. So what's the relationship between 6, 2, and 4 if it's not division? I think there's a better way to do this. Okay, so let's do another example where it doesn't involve base 10. So I picked 21 divided by 7. So if I picked log of 21 divided by 7 should be equal to log of 21 divided by log of 7. I'm going to simplify log of 21 over 7. Well, that would be log of 3, apparently. And I'm trying to see if log of 21 divided by log of 7 is going to be equal to whatever the log of 3 is. So I'm going to need my red. I'm going to plug in log of 3 in my calculator. Log of 3 is going to get me 0.477. So 0.477. And then the log of 21, according to my calculator, log of 21 is 1.322, if I round to the nearest 3 decimal places. And log of 7, if I plug that in, would be 0.845. So if I use my calculator, these are the results that I get for the 3. I'm just going to use common sense. I've got a number bigger than 1 divided by a number smaller than 1. I don't think I'm going to get 0.477. I mean, I could be wrong. Let me just plug that into the calculator. 1.322 divided by 0.845. And that's going to get me 1.564. That doesn't look anything like 0.477, so this is not actually true. So 0.477 does not equal 1.564. So what do you think the relationship is between 1.322, 0.845, and 0.477? Any ideas? I think that if 6 minus 2 is 4, the relationship with the logarithms in a division problem, right? The division inside of a logarithm should be expanded by subtracting the 2. And I think the same rule should apply here, log of 21 minus log of 7. So let me try that. Log of 21, close the parentheses, minus log of 7. I'm going to compare that to log of 3. So I get 0.477. Look at that. So I think subtraction is the way to go. Okay. So now, one more big rule. So the biggest rule, it's actually the most important rule because you'll find out in the next video. What happens if there is an exponent inside of that logarithm's argument? Well, I came up with the basic one for the first 6. In other words, log of 10. 10 to what power is 10 to the first power? So that'd be 1. 10 to what power is 10 to the second power? Well, that's just 2. And then 10 to what power is 10 to the third power? In other words, 10 to what power is 1,000? 3. You get the idea. Well, that's boring. That doesn't really tell me anything because that's just the common log. I'm going to get a little bit more fancy because I don't have any ideas. So let's go with, what if I use powers of 2? So let's say, well, I know that log of 2 is just log of 2 to the first power specifically. And I know that log of 4 can be converted to log of 2 squared. And I know that log of 8 can be 2 to the third, and so on, and so forth. Okay, so I'm going to round to the nearest 3 decimal places. And I bet you that if I can figure out the first log, I can figure them all out. So let's start with the basic. Let's do log of 2. If I plug in log of 2, I'm going to keep it right here. Log of 2 is 0.301. Dot, 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 dot. And if I do log of 4, 0.602. Interesting. Okay, how about log of 8? 0.903. Okay. Log of 16 would be my next guess. 1.204. So I'm just going to take away the calculator and see if I can estimate the next two. So let's just analyze this. I've got the log of 2 is 0.301. Okay, I didn't know that. But then I've got the log of 4 is 0.602. And then I've got the log of 8 is 0.903. And then the log of 16 is 1.204. They're all powers of 2. And yet, for some reason, I see this pattern. It's almost like 301 keeps getting added. Or rather, if I jump steps, if I want to go from 0.301 to 0.903, I literally multiplied it by 3. So I multiplied it by 2 to get to log of 4, multiplied it by 3 to get to log of 8. I multiplied it to 4. I want to see if multiplying 0.301 by 5, so it would be like 1.505, should get me log of 32. So I'm going to plug in log of 32 in the calculator. And I'm going to see if I'm right. Oh, look at that. 1.505. That's awesome. So that's going to be 1.505. And I'm going to see if 0.301 times 6 is, that'd be 1.8, so 1.806. I want to see if I'm right on this one. Log of 64. Oh, yes. Look at that. Oh, man. So the truth is, I didn't know what the log of 2 was, but I knew that I could get to log of 2 to the 6 by using a little bit of information. 1.806. So now I'm going to get my red pen and my black pen. Because remember, log of 2, log of 4, log of 8, log of 16, log of 32, log of 64, they're all involving base of 2. So what I can do is I can take the exponent and pull it out front. So then I know this relationship for all the variables. Sorry, all the logarithms, rather. Let me just put a little relationship for all 6 of these. So all of these relate to log of 2. In particular, log of 2 is equal to log of 2. Well, duh. 1 times log of 2. But log of 4 is the same thing as log of 2, just doubled. And log of 8 is the same thing as log of 2, but just tripled. So 3 log of 2. And log of 16 is literally log of 2, and all that getting multiplied by 4. So 4 log of 2, 5 log of 2, and 6 log of 2. And that is beautiful mathematics. I'm not even going to lie. That's awesome. So let's get everything on one sheet of paper. So these are the big 3 log expansion rules. So just to answer any questions, this is what we're going to be using for the next test, is what happens if there's multiplication inside of a logarithm. So if I have a times b inside of a logarithm, it's not equal to log of a times log of b, but rather log of a plus log of b. So the factors inside of the logarithm get expanded by addition, not multiplication. So that's why it's called the product sum rule. On the contrary, for quotient difference, remember quotient is the answer to an addition problem. So if I have log of a divided by b, so there's an a over b inside of the logarithm, it doesn't get separated by division, but rather subtraction, log of a minus log of b. Okay. And finally, I put an asterisk on this one because we'll find out in the next video. Why is this the most important rule, the power factor rule? So specifically, what happens if you have a to the x power? I'm going to get a pencil just because it's lighter. So if I have an exponent inside of a logarithm Well, that means that the exponent can get factored out to the front. So therefore, log of a to the x can be simplified by making this x log of a. Okay, we'll talk more in detail as to why this is the most important rule tomorrow. Have a great day.